Hi everybody, welcome back. The lighting's not so great here because I just turned the camera here at the bench real quick to do this first part of this video. So I want to start out by thanking a lot of you for all the comments that you gave me on that last Yamaha, whatever you want to call it, Pyramid, the B6 amplifier. Some of those were hysterical. It made my day. I laughed so hard, some of the things you guys came up with, so it was awesome. It was a lot of fun making the video, but it was 10 times more fun watching some of your comments. So thank you all. I want to thank you all for all of your comments and for your well wishes and for the donations you've made to the channel, everything. I really appreciate it. I just want to let you know all that. So I'm a little bit tired. I've been going since about 4 o'clock in the morning. I got called out to a service call, and you can imagine what it's like right now with the current situation, health situation going on. So it was kind of a challenging day, but I'm home now, and it's the weekend coming up. And I sat down to watch a couple videos. And yesterday, one came on by one of my favorite YouTubers called Diode Gone Wild. And he's starting a series on the spark gap Tesla coil. And no sooner did he release that today, Electro Boom came out with another version of a Tesla coil video. And I was reading through some of the comments, and there was quite a bit of back and forth debating about where the spark gap goes and how, if it's important, if it matters at all. And of course, you know, like so often people do, you know, you watch something and then you make a link to it and you say, see, you're wrong here, click this link, you know. But I don't like to do that. I don't like to just watch somebody's video and because they say something, I believe it, and then I go to other people and kind of repeat it. I kind of like to know myself, you know, is it right or not? So I thought, well, maybe I'll make this video. We'll just do a little talking video, spend a little time at the bench here. And first of all, I'm not going to be the one to totally answer the question. Both of those two people are much more intelligent than I am at that subject. And I'm only going to share some thoughts that are going through my mind, and I'm going to pose them to all of you, and maybe we can get some comments going on the comments section where we can talk about some of this and what we think, how this Tesla coil works. It's such a simple circuit, yet there's so much involved in it after you start studying it. It's really fascinating. About 30 years ago, I built a large Tesla coil in my shop that was at my parents' house. I had a 28 by 32 foot shop, and it was pretty well equipped. A lot of the stuff went away when my dad passed away, and we had to sell the house quickly, and I wasn't living anywhere around town and didn't have anywhere to move anything. So a lot of my equipment disappeared at that time, and I've slowly been kind of building it back up over the years. But one of the things I did was I built a large Tesla coil, and it was very similar to the one that Diode Gone Wild had built with the spark gap in that position. But I thought I'd share a few things with you that I'm wondering about, and then give everybody a chance to comment so we can maybe have some debate. Now, once again, this isn't a thing about arguing, and this isn't a thing about criticizing one another. We're sharing knowledge with one another, and I just want everybody to remember that in the comments section, to be kind and understanding to one another and be respectful to each other, so that we can learn together rather than learn to disagree. You know what I mean? Let's try to solve and understand something more deeply than we understood when we first started. So that being said, let's go down to the bench and let's check a couple things out. Okay, for starters, we're just going to do a little bit of a refresher for some of you who are new to electronics or who aren't as familiar with electronics. For those of you who already know this, skip through, feel free to. So I have three components in front. Actually, I have 6 components, but 3 different types of components in front of us. I have a pair of 1,000 ohm resistors. These are resistors. 1,000 microfarad capacitors, and 1,000 microhenry inductors. So we have resistor, capacitor, inductor. And right here, I have my little LCR meter. So the first thing we'll do is we'll measure the resistor. Okay, we're just going to measure one of them. And remember that these little leads that I have in here, even though they're rather short, they still will count for something in some of these circuits. So we measure it, and you can see it is very close to 1,000 ohms. It's 0.996 kiloohms, which would equal 996 ohms. Now, unfortunately, on this meter, you can't change the scale to make it read ohms. It just changes the scale on its own. So 996 roughly ohms. And if I look at the other resistor, it's going to be roughly the same, within a few ohms. 996 ohms. Now, what happens if I take these two resistors and I twist them together? So now the resistors, this is what we call parallel. They're parallel to one another, right? So we've connected them in parallel. And if we connect it up now, what do you think it's going to be? They're both roughly 1,000 ohms each, right? Or 996. And you can see now it's roughly 497. So basically, by putting the two resistors together when they're the same value, it actually cuts the value in half. So putting resistors in parallel makes the resistance go down. So what do you think will happen when we put them in series? So we twist this up, and same thing. Put them in series. I'm just going to hold it. And you can see now it's almost 2,000 ohms, or 2 kiloohms. So when you put them in series, the resistance gets larger. And that's how resistors work. Now, capacitors are just the opposite. And I'm doing this because I've had several of you email me and actually ask me about how this all works. So now we're going to do the same thing with the capacitor. So we put the meter on the capacitor. Isn't this fun? And this is remember, a 1,000 microfarad capacitor. I hope you can see that. And it's roughly 1,000. It's 984 microfarads. And if I take two of them and put them in parallel, do you think it's going to be the same as the resistors? Because remember, we put those resistors in parallel, the resistance went down. So what do you think is going to happen if I put the capacitors in parallel? Think it'll do the same thing? And look at that. 2 millifarad, better known as 2,000 microfarad. So the capacitors act just exactly the opposite of the resistors. So you put them in parallel, and instead of the resistance going down, where the capacitance going down, the capacitance goes up. What happens if we put them in series? I'm just going to hold this. How's that? So it's going to be a little bit off because of my fingers, right? And you can see what happened. It cut in half. It's roughly 500 microfarads. So resistors and capacitors, when they're in parallel and series, they're the opposite of one another. So now we have an inductor. What do you think it's going to do? And we'll measure this. So we can see the inductor is reading as a resistor right now. Let me change it. There we go. And this is a 1,000 microhenry inductor, and you can see it's reading 1,022 microhenries, right? If I take two of them that are both 1,000 microhenries and I put them in parallel, what do you think is going to happen? They act like a resistor. You see that? The value cut in half. And if I put them in series, I'm sure you know what it's going to do. Roughly 2,000 microhenries. So resistors and capacitors, or I'm sorry, resistors and inductors work the same as far as parallel and series with their values, and capacitors are the opposite. So with either of these guys, if you put them in parallel, it makes their value, the total value, go down. And if you put them in series, it makes the total value go up. Whereas with the capacitors are just the total opposite. If you put the capacitors in parallel, it makes the value go up, and if you put them in series, it makes the value go down. Now there is a math formula that you can use when you have dissimilar values. So let's say these weren't each 1,000 ohms. Maybe one was 1,000 ohms and the other one was 500 ohms, for instance, or 470 ohms. There's a math formula, and I'll try to post that on the video here. So you can see. The reason I'm showing you this maybe will come into play a little bit later here. So let's move on to our Tesla coil now. So I have in front of you a couple of diagrams. One of them is the schematic of the Tesla coil that was featured on Diode Gone Wild's website on his video. And the other one up here is the one that was done by Electroboom. And they look very similar, except the main difference is where they put the spark gap and the capacitor. It was very interesting when I read through the comments section on the Electroboom video. Sometimes I'll look through comments because I learn things, because there's some pretty smart people out there that'll put some things down there that make a lot of sense, and that's how we learn. So I started reading through them, and there were countless ones where somebody just put a link to Diode Gone Wild and said, you're wrong, he's right, this is why, here's your thing. But really it got me to thinking, why is either one of them right, wrong, or why is either one of them not wrong? I don't know. That's what I want to talk about, and this is the discussion point. I'm just going to bring up a few thoughts, and then hopefully we can talk about it in the comments section. So first of all, let's look at this first one up here. And now, what a lot of people say when they talk about how one of these things works is they say that basically what happens is this high voltage transformer, as the power starts to go up on it, okay, what will happen is eventually the power will raise to a certain point. Okay, let's stop and talk a minute about the interaction between the capacitor and your source voltage, which is going to be your transformer or whatever. What's happening is that capacitor is actually going to slowly charge at the rate of its capacitance and the rate of the current that can feed into it. So you're going to see a ramp. You're going to see the voltage start at 0, and it's going to ramp up to whatever your maximum supply voltage is. And this is regardless of whether you're using AC voltage or DC voltage. So if it's AC voltage, as the sine wave begins to build up, so too will the voltage on the capacitor build up, and you'll see that charge. If you attach a DC voltage, the same thing's still going to happen. The capacitor is going to charge up based upon the available energy, current from the supply. So this circuit can run on AC or DC. I know a lot of people get confused on that, but that's what's happening. This capacitor is charging up until finally the voltage gets to a potential that it can break down that spark gap and draw that arc that we're needing for the rest of the circuit to work. So I just wanted to clarify that, where it will be able to break down the air gap of this spark gap. at which point you'll draw an arc, okay? Right? That's an arc. That's a lightning bolt. That's a really crappy lightning bolt, but just hang with me here. So essentially, a lot of people describe this as a short circuit, and it's only for a short duration of time. And during that time, the idea is that there is an interplay between the capacitor discharging into the coil and the coil discharging into the capacitor back and forth. I've talked about our friend Eli the Iceman. Eli Ice. Who's Eli the Iceman? Well, if you remember his name, you can always remember how a capacitor and a coil or an inductor will act. Okay, it's called reactance. In an inductor, L stands for inductor, right? L1. The voltage will lead the current. In other words, when I apply power across this coil, the voltage will instantaneously be whatever it is. So for instance, if I put 100 volts from here to here, there will right away be 100 volts. And then eventually, as this will induce a magnetic field. When that magnetic field starts to collapse, what's going to happen at first is the current is going to be resisted by this. And then as this breaks down, the current will start to go up. In other words, this only will resist that current until that magnetic field begins to collapse. At which point this will begin to more and more look like just a piece of wire, a short circuit. The DC resistance on this, if I took my ohm meter like this, and I took my probes and I measured from here to here, ohms wise, this will read almost like a dead short because it's just a piece of wire. It's just a few turns of wire. But when I put a sudden change in voltage on this, I go from 0 volts to, let's say, that 100 volts. The 100 volts will be there right away, but no current will flow at first because there will be an opposing magnetic field that will prevent the current from flowing right away. But as that field starts to slowly collapse, this will slowly start to come back to its DC resistance, and then the current will begin to go up until finally the current will be whatever is limited by the DC resistance of this coil or the DC resistance of the power supply driving it. So voltage leads current. In a capacitor, the opposite thing happens, okay? In a capacitor, the current will lead the voltage. So if I have a 100 volt power supply and it's sitting up here, and I take that power supply and I go right across the capacitor, what's going to happen is at first the voltage will be nothing because this acts like a dead short to that sudden change in voltage. And eventually, as this capacitor begins to charge up, and it's going to draw enormous amounts of current because it's a short, right? And eventually, as the capacitor begins to charge up and it gets closer to equilibrium with the actual charged voltage, that current will begin to drop. So instead of the current beginning to go up like it does in this, the current begins to go down in this one. So they're opposites. They work in opposite manners. And because of that, that's what's causing this frequency to take, or this oscillation to take place. One of them wants to get rid of all of its current, one of them wants to get rid of all of its voltage, and vice versa. And they fight back and forth. And it's kind of like a ping pong match or a tennis match, back and forth with that energy, until finally everything equalizes once again and all the energy is spent. It's not used anymore. Everything's in equilibrium. And then it goes to rest. So that's essentially how a resonant circuit works. And the rate at which that happens is dependent upon the inductance of the coil and the capacitance of the capacitor. So that will determine how fast that oscillation will take place. That's called a resonant circuit. So, and I'm probably doing a really crappy job because I'm kind of firing from the hip on this. But anyway, the whole idea of that is, in a Tesla coil, we want to charge the capacitor and then we want to let it empty into this coil and allow it to oscillate. Once everything kind of wears down, I want to charge it again and then connect it back here. And that's what this spark gap is doing. Now, if we look at how the spark gap works, again, like I said, let's just assume this is a short when that arc happens. Let's assume what everybody's saying is the truth, and this is just a dead short here. Well, if you look at this circuit, we can redraw this circuit a little bit, right? This would be the same as this here, right? That's essentially, because if we put this together, we can redraw this any way you want. It's a parallel circuit, right? So what do we have here? I have an inductor here, and I have an inductor here, don't I? And my current loop is going to be through this circuit, right? And what happens when I put two inductors in parallel? Just like the resistance, this is a different inductance than this one, right? This has much more inductance because this is only running at line frequency, which is 50 or 60 hertz. But this coil is a very small coil. It's designed to oscillate at high frequencies. So you're adding these two coils together, like resistors. You're not adding them together, but this will actually negatively influence this. It will actually change the resonant frequency of this coil because it's not actually the inductance of this coil, it's the inductance of this plus this in this configuration, isn't it? At least that's how I see it. And because of that, you actually have that oscillation going through this as well as through this. And that can feed back, even though this core here doesn't like high frequency, it'll kind of oppose that a little bit because of the permeability of the core, and I'm not going to get into that on this video. But anyway, some of that noise can get back into here, and that high frequency energy can actually break down the insulation of this transformer winding. At least that's what I was always taught. Now, let's look at this one up here. If we look at this one, we'll do the same thing. Let's say this shorts out. So you have your arc, right? So the voltage builds up. Okay, so we have a sine wave, right? That's what this is coming here. And this is high voltage. It's 0 volts. And this is, let's say, 12 kV. Or 12,000 volts. When this gets up to about 10 kV, because of where our gap is set, this draws an arc, let's say. When this arcs out, let's say, once again, theoretically, this is a dead short. What do we have now? Since this is a dead short, it is a much lower resistance or lower impedance than this coil. So essentially, this looks like one giant short, and your entire loop is right here. So now you're only dealing with your capacitor and your coil. You see the difference in how the circuits work? They both will oscillate. But if you're using the math formula, the quarter wave rule, and you're trying to calculate this accurately for what frequency it will resonate at, in this one, you have to take into account what this is going to be. And it could be anything, because there's a lot of weirdness going on here, because you have this coil, plus you have the core, plus you have the primary, plus you have whatever connected to the mains. And usually they put suppressor coils here to suppress the RF from getting back into your mains and all that. We'll get into that later. But in this circuit, that's not the case. So this is why I believe that this is the correct one. Now, don't ask me, let's ask Nikola Tesla. So what I have in front of you now is a few pages I printed from his Colorado Springs notes. So in 1899, I believe it was, Nikola Tesla rented some property up in Colorado Springs because it was way up at high elevation. It had a lot of electrical storms and so forth, and he wanted to study the ionosphere. And this was one of the ways he could do it. And he wanted to use some of his apparatus and try to energize the ionosphere. Now, anybody who actually has taken the time to read through his Colorado Springs notes, you really begin to see the truth of what he was doing. Again, like, there's a lot of Google scholars out there. You know, you've heard me use that word before. Somebody that'll Google search something, they'll see a comment or a post that somebody puts on some web page somewhere, and then they repeat it to others and say this is what it is. But honestly, you know, and a lot of things are said about Nikola Tesla. He's a very controversial character. I mean, he did a lot during his career, and there was a lot of other people at the same time equally as intelligent doing things, and there was an amalgamation of people working on technology at the time. It was really a very prolific time in our history for electronics, and he was just a part of it. But some of the things he did contribute were brilliant, in my opinion. Now, you can read through some of this, and he's talking about, he's using direct current on this. And again, you can use direct current or alternating current, because the way these capacitors and coils work, they're AC anyway, and they just need a repetitive charging of this circuit to continue it working. Now this one is using DC, and he's using a very precisely timed spark gap. And that spark gap is more like a set of brushes on a commutating wheel with little fingers on it. And it would pulse this at a very regular rate. And you can see here he had a little adjustable capacitor with a feed horn. This was actually a little radio circuit that he was experimenting with up there back in 1899. Now, Marconi was already doing some of this, you know, earlier. And I'm not going to get into the whole argument over dates and times and people and all that, because it's just worthless for me. They all had something to contribute to all of this. They all worked on this stuff, and they were all interested in it. But anyway, what I'm showing is you can see where he put his spark gap or his commutator. It's across the source. Now, this is the interesting part when you get to this. Here's your high tension transformer. So this is your primary, and then you can see the small turns of the secondary. So this would be like your neon sign, your driver transformer. And you can see he very distinctly has this, he has the spark gap on the other side of the cap. So this is like the electro boom version. So the scheme of connections illustrated in Figure 1 has the disadvantage that the primary discharge current passes through the break. Hence, the resistance of the latter being large, the oscillations are quickly damped, and there is besides a large current through the break, which makes good operation of the latter difficult. To prolong oscillation in primary and increase the economy, one of the schemes before considered may be resorted to. One of these is illustrated in Figure 2, which follows. In this arrangement, the currents through the brake device are much smaller, and the oscillations started by the operation of the brake in circuit LPCP continue much longer. Okay, and then he goes into explaining why this works. So all throughout all of this thing, he's trying different circuits. And you can see now he's using two capacitors like this and an inductor here. But you can see very rapidly he moves his spark gap to across this to shunt this part out right here. And that's kind of the point that I'm making. And again, it all works. They will oscillate, but there is reasoning why why one has an advantage over the other. Now, last but not least, let's talk about this spark gap. When I studied this spark gap is not really a dead short when this shorts out like this. When this arcs over, it was explained to me that this is more like a semiconductor than it is a dead short. In other words, and you could see he kind of alluded to that in that comment that I read earlier, where he talks about that the discharge current passes through the break. So if you go to this other version here, let me dig it out. Where did I put it? This one right here. What he's saying is that the discharge current is going through the spark gap this way. And of course it is going the other way too, but since that spark gap is in parallel with this coil, it changes how this thing works. And again, this spark gap doesn't exactly work like a dead short. This is basically plasma across here. And even though it may have a relatively low DC or resistance, it still does have resistance. And also it reacts more like a semiconductor. It doesn't pass current in the same both directions like a piece of wire would. I hope that makes a little more sense. At least that's the way I understood it. And again, I'm just telling you what I learned, and that this is someone who is not a physicist and does not know all these things. And I'm kind of putting these ideas out there, and I want to hear from all of you what you think. What is this spark gap? Is it a dead short when it arcs over, or does it work more like a semiconductor? What are the properties of that spark? That's what this is really all about. This is much more important. You know, you look at some of these other ones that he gets into where he's using these. If you read through here, he talks about what these are, and he's actually using carbon contacts, and he says they're loosely touching. He talks about it. I don't know if it's in these pages that I printed, but when you read about it, he talks about how these are actually touching. They're not as much of a spark gap as these open air spark gaps are. So there's a lot more to this, you know. So anyway, that's my 2 cents on all this. And I believe this is the proper layout. And like if you go to some of the big companies that do this for a living, like Electronics Unlimited is one, or Information Unlimited was a company I used to deal with. They were in the back of the science magazines. You can order Tesla coil kits and Tesla coil plans. This was before the internet. I'm dating myself a little bit. But you could order their catalog, and they actually would sell plans for Tesla coils. And all the ones that they had, and I have all that stuff somewhere. I'd have to dig it out. I don't know where it's buried, but I have a lot of books and things on it. But it's always this design here. It's rarely, if ever, do you see this design here. So please comment. I mean, honestly, be kind. Don't criticize and insult one another. I very much dislike that, and I will delete those kinds of comments. But talk about it, and let's try to learn together. So that's it. I'm tired now. It's been a long day, and got to spend a little time at the bench with all of you. And as always, I wish you all peace, joy, happiness, and good health in your lives. Hoping that all this stuff goes back to normal soon. But one thing I can say is it's been giving us more time around at home with our families and to do our hobbies and things like that. So I guess every cloud can have a silver lining if you want to look for it. So anyway, I wish you all well. Stay well. Thank you all again, as always, for the good comments and everything. and we'll see you again soon. Take care. Bye-bye.